I think the real value of it, though, is the fact that I reference a lot of good sources, some sources of good electrical diagrams, some good tips from videos that I've watched, and explaining how my system is different from these other systems that have been documented pretty well. I hope you'll find value in it. My real goal in it is to get some feedback from you, telling me where I've gone wrong, or maybe some of my ideas that you think are good, or whatever. But in any case, I'd really appreciate your comments if you'd comment below, and if you'd subscribe and get notified when I post new videos. I have lots of questions, and I need all the help I can get, so please help me. Thanks. This is my video about my electrical system, and what I've done is I've borrowed from 3 of the best sources that I could find on designing your electrical system, and then I've modified it to suit my situation. So I'd like to talk first a little bit about the sources that I've used. The first one is from Explorist.life by Nate, and actually he is an affiliate of, actually all these sites are affiliate sites. So, all of the equipment that they mention here, they're getting a little bit of a cut, which is not a bad deal for the amount of information that they give you. But I did buy my my electrical solar setup, my inverter charger, my charge controller, my batteries and everything from Battleborn, and through Nate's link here, and so he got a little bit of cut of that pretty sizable purchase, so I'm glad to have steered that his way. And he's provided this electrical diagram, which I have used extensively, if not for exactly the cable sizes and specific equipment that he's got here, because my situation is different, but functionally it's really a good guide to use. And this is at Explorist.life. Another source that I thought was really good was from faroutride.com. Okay, and they've got an electrical system here, and you can take a look at this, or you can pay them a little bit of money for a tutorial and a download for this stuff. And this is very similar actually to Nate's wiring diagram, and they've all got interactive components here to show you the various equipment and what their loads are, etc. And then the last item or source that I used was from Ken at Caravan, and he built a Sprinter. All of these guys have excellent websites, and I recommend them highly. The Far Out Ride guys especially have a lot of really good explanatory information on them. But there were still questions that I had after going through all of this stuff, and so therefore I thought there might be something left on the table for me to contribute, at least as far as my understanding or misunderstanding of these concepts. And the reason I'm doing these videos is not necessarily to gather affiliate links or clicks, but to try to motivate you to ask questions of me and question what I'm doing, so that to prevent me from making a mistake or to save me from myself. The other thing that I used quite extensively here is the Circuit Wizard from Blue Sea Systems, which is kind of a little calculator, and we're going to be working with that in a little bit here. But anyway, so that's where we are, and let's start out. What I'd like to do is just kind of examine each major branch of the electrical design and talk about how my situation is a little bit different, given that I'm using my vehicle is a ProMaster City. It's a very small space. The distances are very short. I've got a particular size alternator. And so my cable sizes, I questioned all of the cable sizes and fuse sizes and utilization of breakers, etc., in all these diagrams to come up with my own unique design. Now, I don't have a diagram, so I'm going to borrow on their diagrams. These are, amazing. You can click on these things and get all the information that you want, even down to the lugs. You know, they've got affiliate links to the Amazon site, which is great, but nevertheless, as I said, mine is a little different. So I'm going to start off by first looking at this circuit here, the alternator to the battery. And what makes this unique actually is this little device right here, which is the battery isolation manager that Battleborn sells. And so let me show you how it functions actually. This is a device that goes between the chassis, or I call it the engine battery, and the coach battery. So this is the alternator circuit where we're going to be charging our coach battery from the alternator. And it's got a couple of inputs here. You know, the ignition switch, you have to connect up to it, and then this is a option that allows you to with a momentary push button you can bypass the relay and make a direct connection between the battery coach and the engine coach, or the the coach battery and the engine battery. And that's what that's all about. But other than that, the thing that's important here is to understand how this little device works to safeguard your system and to work with your alternator. So this is information that I got from Battleborn. The scenario number one is that the engine is on, okay, with the engine battery voltage greater than 13.4 and the coach battery less than 13.3. Okay, so then what happens is that now it's measuring those with this relay open circuited, obviously, because when it's closed, those voltages are the same. So that's the first thing to recognize. So as soon as the open circuit voltage is measured as 13.4, greater than 13.4 on one side, on the engine side, and less than 13.3 on the coach side, then the Li BIM will connect the batteries for 15 minutes. Okay, then disconnect the batteries for a wait time of 20 minutes. Now this is how it's being easy on your alternator. After this wait time, a new voltage reading will be taken of each battery. In other words, it'll open up it'll measure that voltage with an open circuit, and then if the voltages remain within the scenario's parameter, the response repeats. So as long as that, let's suppose that your coach battery is dead, it's going to take a while to come up to voltage, right? So it will cycle on for 15 minutes, then off for 20 minutes, then on for 15 minutes until it brings that coach battery up to the acceptable voltage. Now, another scenario is that the engine battery is below 12.5 volts and the coach battery is greater than 13.5 volts. Okay, in this case, this isolation manager will connect the systems together for 1 hour, and in this case your coach battery is actually charging your engine battery. Then disconnect the batteries for a wait time of 2 minutes. Then it measures the open circuit voltage again. After this wait time, a new voltage reading will be taken of each battery. If the voltages remain within the scenario's parameters, the response repeats. And I'm sure that the ignition switch logic is integrated into that, because it's not going to, if the ignition switch is open, it's not going to do all this, right? It's only if the ignition switch is well, I don't know. That's a good question. Actually, maybe it will. But I don't know if you can charge the engine battery with the ignition switch open or closed. That's a good question to ask them. But in any case, that's kind of the way this thing works. It closes and then it opens and it measures the voltages, then it closes, then it opens and it measures the voltages again. All right. So my choice in this scenario was to do something similar to what was done by Lee Blake and Jamie of Enigmatic Nomadics, where they installed, this is a sample build on a system which is actually fairly similar to mine. And here's the isolation manager, the BIM, battery isolation manager, that they mounted in the engine compartment quite close to the battery. And that is something that I'm probably going to do as well. So that's the situation there, and I'll provide that link down below so that you can get a better look at just exactly how they configured it. And they used a cable size which is, I think it was number 4 that they're using. And that was my big question, was how should this thing be fused, and what size cable should be used for it. All right, now this is where I have a little bit of an issue that I'd like to discuss with everybody here. So let's suppose that we're interested in calculating or determining what size cable we need to connect between the alternator and the coach battery. And this is kind of the situation. You know, if it's 14 volts, it's greater than the voltage that the BIM will sense to close the relay, which is right here, to close this switch to connect the alternator to the coach battery. Okay, so let's assume that that's true. Now let's, just for kicks, let's assume that this is really a small wire. Okay, and also that the coach battery is nearly dead. All right, and my alternator in the ProMaster City is 160 amp alternator. So let's assume that we're going at 150 volts. Now, if this is a small conductor, we're going to have a large voltage drop across here, right? And so therefore, this voltage, when we close that switch, the voltage available to pull the coach battery up is going to be pretty low. But just for kicks, let's see what the circuit wizard has to say about this. Let's put in like a 12 volts and load current of 150 amps. Now the length of conductor for my vehicle is going to be, it's about 12.5 feet. Okay, so I have to double that for the positive and the negative return. I'm not going to use the chassis as the negative return. And so therefore my length of conductor is going to be 25. Okay, and the answer is 2-aught cable, and we can explain the results. We see that if we just look at the ampacity, it would be in number 4 would be plenty big. Okay, but if we're interested in keeping it to a 2% voltage drop, which is what or 3% voltage drop is what I showed there, 150 amps, then it calls for a 2-aught cable. Well, a 2-aught cable is pretty doggone big, right? And pretty heavy. So I'm just wondering about that. One question I have is 150 amps is going to flow, but it's not going to flow for very long, right? And in fact, if we assumed that, for example, that voltage comes up, and that's one of the things, if the voltage comes up so that the current is maybe 20 amps here instead, all right, then if you calculate it, it says a number 8 is plenty big. And again, it's the voltage drop that is really determining. You know, the capacity, the ampacity is not an issue. What's really driving the cable size here is the voltage drop that you get. So a number 8 is pretty skinny, and you know, you have to think about, this is not really a constant circuit here. You know, it's the voltage is coming up. When it's low, you get a large voltage drop across this with a large current, but you're bringing the battery voltage up. Now, you're never going to be able to, it's going to take a long time because you're going to have a smaller current, because of the very small wire, and the lower the impedance of this wire, in other words, the bigger the wire, the more this voltage is going to match this voltage trying to pull the coach battery up. So the point here is that, in one situation, assuming a large current flowing, it calls for a 2-aught cable. In the other situation where the coach battery is not really all the way dead, it would call only for a number 8. All right, so basically there is no right answer to this. How long will it take for the coach battery to build up, and under what circumstances are you willing to connect your alternator? So, for example, if you've got if you want to let your coach battery go all the way dead and then try to charge it all the way up from your alternator, there's going to be a large current. It's going to be hard on your alternator, and I'm not sure that that's a mode of operation that I'm willing to tolerate. So that might cause me to put in maybe a 150 amp fuse in this thing, and assume that I'm never going to have my coach battery all the way dead. Now, if I assume that my coach battery is not all the way dead, then I can assume a lower level of current being used to charge that coach battery, and therefore I can get away with a smaller cable. So somewhere between 2-aught and a number 8 would be a cable which would be sufficient. Now, I can't tell you precisely what that's going to be, but I asked Battleborn about this situation. They recommended a 1-aught cable. So that's what I'm going to use. I'm going to install a 1-aught cable, and then I'm going to monitor exactly how this system behaves, and measure the alternator current, when I am charging the battery, and see how that works. But I feel fairly confident that using a 1-aught cable, I ought to be able to make this work. Now, again, my device is located in the engine compartment. So these cables here are very, very short. This cable is about 12.5 feet long, and so I'm going to make all of this cable 1-aught cable. The fuse I'm going to put in here is going to be 150 amps because I don't want anything over 150 amp. 150 amp is way lower than the capacity of the cable, but it's going to protect the alternator more than the cable. So I'm putting in that fuse to protect the alternator and the battery here rather than the cable. So I'm going to choose 150 amps and 1-aught cable for this circuit. And then a fuse and a disconnect. Now, one of the differences between what I'm doing and what Nate has here is he's got a separate fuse and a separate disconnect. And the disconnect that I'm choosing to install looks like this. It's somewhat similar to that, but it's a lot cheaper than the other disconnect. But the other thing, which is really sort of neat and important to me, is that I can attach onto one of the terminals of this switch a terminal fuse block, which is this kind of a thing. All right, it looks like this. Is a better picture of it down here. Basically, you put this over the stud, and then you connect your cable here, and there's a fuse in between. So these are the fuses that you can buy for that. And the advantage of this is that you don't have a separate cable between your fuse and your disconnect switch. Okay, and if you're working with a very small box, then that's a pretty nice arrangement. Okay, so that's what I'm going to do a little bit differently. The other thing that's important is to have actually the disconnect switches and the 12-volt distribution panel accessible inside the van, but still out of the way. Okay, so that is one reason why I'm going to basically, let's bring up the CAD drawing here. Okay, here's the CAD drawing, and this is my assembly down here. So let's actually get rid of the couch there, and actually let's get rid of all the other stuff there too. So and take a closer look at this. These are those little switches that I'm talking about right here, represented along this bar. And remember that the couch covered this thing. It's on top of it, right? So one thing I want is I want them out of the way, but I want to be able to, for example, reach under the couch and then operate these switches. I don't want them sticking out where I have other stuff on either side of this thing, or I don't want it on the door. And here's my 12-volt distribution panel with the fuses that I'll have available to me. And the other consideration, that there are actually two more considerations which are important to me. One is the batteries. And I'm going to create this rack so that I can remove these batteries pretty easily, because I'm not confident that I may be in situations where I'm in really cold weather and I'm maybe inside for a week and the van is parked out somewhere. I want to be able to go out and bring those batteries inside. I don't want them in the sub-zero cold, or similarly in a really hot environment. I don't want them out there for a long time. I want to be able to easily disassemble this thing and pull those batteries in. So taking a closer look at this assembly, let's get rid of the all of the equipment in there, and look at this. What happens is there are rods holding pieces of L-channel aluminum together, which will hold the batteries and the inverter charger in place over here. And then there are a couple of flat aluminum bars here and here, which will hold the terminal blocks, the bus, positive and negative bus. And then there's space over here for my charge controller to hang off of this in this space. And I can put my shunt down here, and what else was there? Let's see. Oh, the AC breaker can be located right there, and the batteries, and it's all accessible, and I can take that all apart because these are all going to be bolted. These are threaded rods holding these together. Okay, so I can take them apart, and I can really torque them down so that they hold all of these elements in place, and the whole assembly is going to be, attached to the floor of the van. So this is the sort of the electrical rack that I'll be using for this. The other thing that's important is that there's going to be, right here is a ventilation hole, and that really it determined the location of the whole rack assembly within the van. The reason is because looking at it from the bottom, you can't see it from there. Okay, but on this side you can see it. Let me use a different view. Do the 2D frame, I guess, so that we can see that better. But these holes are located, there aren't very many places in the floor panel of the van where you can locate a 3-inch hole. So I've located the 3-inch hole, and then I have basically created or I've located the rack in a location so that the hole is in between the batteries. Okay, and so air will be pulled in from the bottom below the van, come up, it'll flow through here. It'll flow. There's a fan inside the charger inverter which will push the air out that direction, and then also out this direction, and then it'll be exhausted by my MaxxAir fan. Okay, so that's the way that's going to work. Okay, so let me talk a little bit more about these other paths here. This other path is from the PV panel to the charge controller. Now, one thing I notice in here are the use of circuit breakers, DC circuit breakers, and I'm not a big fan of DC circuit breakers. With DC there is no current zero to interrupt. Most circuit breakers operate, they disconnect, or the arc is extinguished inside the load break when the current reaches a zero. That's true for AC systems, alternating current, because the current is represented by a sinusoid in which the 0 point is, you go through the 0 point twice each cycle. All right, well, for a DC system you don't have that, and that's why when you pull the switch on a DC switch or breaker, you're going to draw an arc until you actually extend the switch sufficient length to dissipate that arc in the air. You know, for that reason, I really don't like DC breakers. I don't think they're well designed. I'd rather use a fuse combination where if I have an overload, it's going to burn that fuse, it's just going to keep burning that fuse until it opens. All right, so I'd rather use a fuse, but in this case, I think it's important to understand that between the photovoltaic panel and the charge controller, now this is at a voltage, in my case, of about 40 volts, between 30 and 40 volts, and the current is less than 10 amps. And even if you short-circuited this photovoltaic panel, you would get no more than 10 amps. So you're never going to have a problem protecting these cables. These cables can never carry more than 10 amps for a short circuit located anywhere in this circuit up to the charge controller. And for that reason, it really doesn't make sense to even have a circuit breaker. I mean, a load disconnect is fine. You don't need to have a circuit breaker. You don't need to have a fuse on this portion of the circuit. All you need is a disconnect. For the same reason, you don't need it, because if you have a short circuit on this side of the charge controller cannot contribute any current to the short circuit. Okay, so I asked Victron whether you could pass short circuit current through the charge controller. They said no, it's not going to happen. So there's really no reason to have a fuse or circuit breaker protecting these cables on this side of the charge controller. On the other side of the charge controller, it does make sense to have a fuse and a disconnect. All right, so that's the situation I'm going to have now. Nate calls for 10 gauge cable here, and I agree. I'm going to use 10 gauge cable, even for very long lengths, because I'm going to have an extension cord. I want to be able to pull my PV panel out and maybe locate it 25 feet away. So for a 50-foot cable, 25 feet out, 25 feet back, you can still get away with 10 gauge, you know, at these low currents. You may experience a little bit more voltage drop in that situation, but I'm willing to try it to see if I can tolerate the voltage drop across that cable to still charge my batteries. Other than that, the other sort of elements of this system are similar. One thing to understand is that each battery can only contribute 100 amps. So we're going to get at maximum 200 amps feeding our inverter to create AC. And so therefore, you know, a 250 amp fuse is plenty fine to protect this cable. And I'm also using 2-aught cable all throughout where Nate has specified 2-aught cable here. These cable lengths are so short, it's all within my box that I just showed you, that it's really not an issue. There's no reason to go any less than 2-aught. So that's fine. And what else? A battery to the bus, a 250 amp. Again, same reasoning. Okay, no more than 200 amps coming out of these batteries. You have to understand each one of these batteries also has its own protection, under voltage, over voltage, and current, I believe. So again, this 250 ampere fuse here is just protecting, you know, the cable. And again, I'm not using these separate fuses. I'm going to be using those terminal fuses as I showed you earlier, and I think those will work pretty well for me. Yeah, and so that's that. Oh, the other thing is Nate has specified here a Romex for this cable. Everyone else that I've seen does not recommend you use Romex for your AC cable. All of this cable in all of this diagram is marine grade stranded copper. And the reason for that is because of the vibrations that you experience inside the van. You don't want your wires coming loose. You have to terminate them correctly. And Romex just is solid conductor, 10-2 or 12-2 or 3. Romex, this should be 10-3 actually, is just not going to work very well. The other difference that in my situation is I'm not going to have a 30 amp connection. There's just no way that this is going to support 30 amps, and so I'm just going to have a regular 110 volt plug here. And if I come to a situation where I need a 30 amp type plug, I'll create some kind of an adapter or something for that. So that's pretty much my setup. There are a couple of other things. I really recommend this video that Lee Blake and Jamie from Enigmatic Nomadics created. In this one, Lee is talking about this stripper.
What's in there? A little blade? What is it that's doing the cutting? What is that?
It's a blade. And so what you do is you cut it around, and then when you take it off, you flip it 90 degrees, and it cuts that little.
So there was no link in this video to this device, so I just wanted to locate it, or I wanted to show it to you. I found this on eBay. eBay was the lowest cost that I could find for this kind of device. There are various cheaper ones that are cheaper grade material, based on the reviews and everything else. I thought that this Encore Premium Cable Stripper was the best deal for 25 bucks. Another thing that Lee talks about in this video.
This is copper shield, which comes in a jar with a brush, and there's no way to use it without getting goo all over yourself. So I stuck it into this irrigation syringe.
And the copper shield is a substitute for what you see on YouTube quite often is people are soldering, their terminal connections. So you got a blowtorch and you're going to heat it up. You're going to solder. You're going to suck solder into the terminal with the cable to create a moisture barrier and minimize corrosion. Well, that whole thing you can replace that, at least according to Lee, and I actually believe him, with this substance here, which again, there was no link for it, and you don't spell it C-O-P-P-E-R, it's K-O-P-R-shield. So I would encourage you to take a look at this. You can search for it on the internet. It is quite expensive. I think it was $28 for 16 ounces of the stuff. But nevertheless, if that replaces all of the work and doing the soldering and the propane torch and everything like that, I think it's a pretty good deal. So I think that wraps up everything that I have to say. I have really benefited from all of these folks. I'll put all their links down below so that you can explore them further. But the electrical system is pretty complex. Obviously, there are a lot of variables that are unique to your situation, and so you need to learn enough about this so that you can design your own system, satisfy yourself that your system is going to perform adequately.